Hello everyone. So we are now on CE 510 Foundation Engineering, and we proceed with our first discussion, which is on shallow foundations, ultimate bearing capacity. So before we discuss ultimate bearing capacity for shallow foundation, let us try to identify the learning outcomes. So at the end of this module, the students are expected to identify and discuss all parameters required in the determination of bearing capacity of soil below a shallow foundation. Number two, to formulate and evaluate the associated bearing capacity factors. Three, determine the design considerations and principles for the ultimate bearing capacity of shallow foundation. Four, compute the ultimate bearing capacity for shallow foundation. So basically, the concept here is the ultimate bearing capacity for shallow foundations. In foundation engineering, we have what we call shallow foundation and deep foundation. So when you talk about shallow foundation, meaning to say this is your footing, your foundation is consideration is not greater than 3 meters. So greater than 3 meters, the depthness is now being considered as deep foundation. So we have, basically this is ultimate bearing capacity for shallow foundation. When you talk about ultimate bearing capacity, we're talking about the maximum pressure that can be supported of the foundation without any failure. So take note that ultimate bearing capacity is the theoretical maximum pressure which can be supported without failure. So when we talk about bearing capacity, it is the allowable bearing capacity is the ultimate bearing capacity divided by a factor of safety. You have to take note that for ultimate bearing capacity, that is being referred to as the load per unit area of the foundation at which shear failure in soil occurs. So for this chapter, for module 1, we will be discussing the fundamental concept of the development of the theoretical relationship for ultimate bearing capacity of shallow foundation subjected to centric vertical loading, the effect of the location of water table and soil compressibility on ultimate bearing capacity of shallow foundation subjected to vertical eccentric loading and eccentrically inclined loading. So basically, to perform satisfactorily, shallow foundation must have two main characteristics. So they have to be safe against overall shear failure in the soil that supports them. They cannot undergo excessive displacement or settlement. When we talk about excessive, it is relative because the degree of settlement allowed for a structure depends on several considerations. So when we talk about shear failure, of course, we know that shear failure is a failure that takes place due to insufficient of shear resistance available between the materials. So shear failure can be determined by cracking of excessive deflection and development of cracks, which gives us advanced warning about the probable occurrence of shear failure. So shear failure occurs along a plane when the shear stress exceeds the strength of the soil. So meaning to say, if the load that is being carried cannot be resisted, there will be an occurrence of shear failure. So for this to start, we have three types of shear failure. The first one is we have what we call the general shear failure. Of course, if you try to consider, you have an illustration, if you try to consider strip foundation with a width of B, so you have here a strip foundation having a width of B resting in the surface of a dense sand or stiff cohesive soil. So if the load being applied to the foundation, if the load, there is a gradual application of the load on the foundation, the settlement will increase. So basically the variation of the load per unit area with the foundation settlement on the foundation denoted by Q as shown here on the figure. At a certain point when the load per unit area equals Q sub U, so meaning to say if the load per unit area Q is equal to Q sub U, then a sudden failure in the soil supporting the foundation will take place and the failure surface in the soil will extend to the ground surface. So this load per unit area Q sub U is usually referred to as the ultimate bearing capacity of the foundation. So meaning to say for this illustration, this is if there is a sudden failure in soil that took place, this is what we call as the general shear failure. So this is an illustration for a general shear failure. So meaning to say you applied a certain load, basically there will be an increase on the settlement. When your load per unit area Q is equal now to the ultimate bearing capacity Q sub U, and there will be a sudden failure in the soil that will take place, this is what we call now as general shear failure. So when you talk about general shear failure, it occurs in dense or steep soil. The total rupture of underlying soil, there is a continuous, so for this one, so the total rupture, it occurs on the so you have the total rupture, it occurs on the underlying soil. There is a continuous shear failure of the soil from below the footing to the ground surface. So meaning to say, the shear failure extends from below the footing to the ground surface. So this is the shear failure. It extends from the footing, below the footing towards the ground surface. So this is the extension of the shear failure. So it pushes the soil on both sides of the footing. So this one, both sides, it pushes, the shear failure pushes the soil from this side and this side. So it pushes the soil on both sides of the footing. So this is an illustration for our general shear failure. So the second type is what we call as local shear failure. So in the foundation under consideration rests on a sand or clayey soil of medium compaction, an increase in the load on the foundation will also be accompanied by an increase in settlement. Of course, if there is an increase on the load on the foundation, settlement will also increase. However, in this case, the failure surface in the soil will gradually extend outward from the foundation as shown by the solid line. When the load per unit area on the foundation equals Q sub U, movement of the foundation will be accompanied by sudden jerks. A considerable movement of the foundation is then required for the failure surface in soil to extend to the ground surface, as shown in our broken line. The load per unit area of the soil, the load per unit area at which this happens is what we call the ultimate bearing capacity, which is Q sub U. Beyond that point, an increase in load will be accompanied by a large increase in foundation settlement. So beyond our Q sub U, there will be a large increase of foundation settlement. So the load per unit area of the foundation is referred as the first failure load. Take note that the peak of value of Q is not realized in this type of failure, which is called the local shear failure. So for the local shear failure, the rupture of the soil only immediately below the footing. So you have here the footing at a certain width B. So the rupture, this is the rupture, this is the failure zone. So meaning to say, if this is the failure zone, the rupture of the soil only immediately below our footing. So there is a soil bulging on both sides of the footing, but at the bulging is not as significant as in general shear failure. So there is bulging in local shear, there is bulging of the soil in the local shear failure, but this is not as significant as compared to the general shear failure. So for local shear failure, it occurs at a soil that are in medium dense or firm state. So this is an illustration for our local shear failure. The last one is our punching shear failure. So this is an illustration for our punching shear failure. If the foundation is supported by a fairly loose soil, the load settlement plot will be like what is shown in this figure. In this case, the failure surface in soil will not extend to the ground surface. Beyond the ultimate failure load Q sub U, the load settlement plot will be steep and practically linear. This type of failure is called the punching shear failure. So for this one, this is an illustration for punching shear failure. So for punching shear failure, the soil outside the loaded area remains relatively, and there is a minimal movement of the soil in both sides of the footing. So the deformation is directly below the footing. So if you're going to observe, this is the failure surface, this is the footing, so the deformation is directly below the footing. So for punching shear failure, it occurs on loose or soft state soil. So this is an illustration now for our last failure, which is the punching shear failure. So this is a certain study that was conducted by BESIC, conducted several laboratory load-bearing tests on circular and rectangular plates supported by a sand at various relative densities of compaction. So this is this is a figure showing the mode of foundation failure in sand. So this was also conducted by BESIC during the 1973. So for this one, for square foundation, B is equal to L. For circular foundation, B is equal to L, which is equal to the diameter. So this is an experiment that was conducted by BESIC. So we move on now to Terzaghis bearing capacity theory. So for Terzaghi during the 1943 was the first to present a comprehensive theory for the evaluation of the ultimate bearing capacity for shallow foundation. So according to Terzaghi, he defined shallow if the depth d sub f is less than or equal to its width. So meaning to say, according to Terzaghi, his definition for shallow foundation, if the depth or d sub f, the depth of embedment is of the footing or the foundation is less than or equal to the width, so that is shallow foundation. However, there are investigators that conducted a certain study, and they have suggested that foundation with d sub f, depth of embedment, equal to 3 to 4 times the width may be defined as shallow foundation. So this is the modification for some investigators on the definition of shallow foundation. According to them, that d sub f, or the depth of embedment that is equal to 3 to 4 times the width, it can be defined as shallow foundation. Terzaghi suggested that for continuous or strict foundation, one whose width to length ratio approaches 0. The failure surfacing soil at ultimate load may be assumed to be similar, so that as shown in our figure, the effect of the soil above the foundation may also be assumed to be replaced by an equivalent surcharge. So that equivalent surcharge is denoted by, meaning to say that the effect of soil above the bottom of the foundation, the effect of soil above the bottom of the foundation can be replaced by an equivalent surcharge, which is Q is equal to gamma times d sub f. The failure zone under the foundation can be separated into 3 parts. So we have here the illustration for the bearing capacity failure in soil under a rigid continuous strip foundation. So this was studied by, according to Terzaghi. So based on his analysis, based on the equilibrium analysis, Terzaghi expressed that the ultimate bearing capacity is in the form of this equation. So he proposed that for continuous or strip foundation, this is the equation. Ultimate bearing capacity is equal to C prime n sub C plus Q n sub Q plus 1/2 gamma B n sub gamma, where our C prime is our cohesion of soil, gamma is the unit weight of soil, Q is our gamma times d sub f, and NC, N sub Q, N sub gamma, those are bearing capacity that are non-dimensional and function only for soil friction angle. So for the bearing capacity factors, N sub C, N sub Q, N sub gamma, this can be defined using this equation. So for square foundation, this is the formula for circular